In this module, we will briefly talk about what are called heat pipes, and heat pipes are quite often used in electronics packages, and they capitalize on liquid to vapor phase change to transport heat from location A to location B, and they are quite effective in transporting heat from a point to another point. And if you replace that heat pipe with a copper, and if the heat pipe is well designed, and in many occasions the effective thermal conductivity of the heat pipe will be at least twice to 5 times that of a copper. For example, if copper thermal conductivity is 400 watts, if the heat pipe is well designed, then the heat pipe thermal conductivity could be close to 1500 watt per meter Kelvin. So, that is why heat pipes are effective, but they by themselves do not dissipate heat. They are meant to transport heat from location A to location B. So, here are some examples shown on this figure. There are heat pipe based water heaters, solar water heaters, solar collectors, and there are what is shown on the left hand side is a heat sink that is mounted with a copper based structure, where this is the so called thermal interface material that would make contact with the electronic device, and this is the heat pipe. So, the heat is carried from this location to this location, and the heat sink mounted here, you can see some fins here, would dissipate. So, this is the advantage of a heat sink, is to carry heat from here and take it to a location where it can be dissipated much more effectively or provide a larger area for heat spreading. So, what happens in heat pipes? Heat pipes are nothing but metal tubes filled with liquid, and there are many varieties of these. Initially, in very old heat pipes, it is purely a metal tube, and gravity assisted operation was carried out, and they are called thermosiphons, Perkins tube or thermosiphons. In current day modern heat pipes, there is a wick. So, there is a evaporator, there is a condenser, and the evaporator evaporates the liquid and changes phase from liquid to vapor, and the vapor travels down to the condensing end, where there is a heat sink mounted, and that condenses the vapor back to liquid, and the liquid that is condensed is brought back to the evaporator by natural circulation and by using capillarity of a wick. So, that is the typical process, is heat that needs to be transported from point A to point B is dissipated or used to convert liquid to vapor in the evaporator, and the vapor travels down to the condenser and condenses there using, at the condenser end is often mounted with a heat sink that is cooling the condensing or condenses the vapor, and the liquid is brought back either by gravity or by capillarity or by other means as well. So, this is the natural circulation loop in a current day heat pipe. And if you look at what are called thermosiphons or the Perkins tube, which is one of the very early devices that was designed, they used gravity as a way of bringing the liquid back. And it is shown on the figure here that heat input is happening at the bottom of the tube, and the thermosiphon is an evacuated metal tube filled with little bit of water or liquid, whatever it is. Other liquids can also be used, and as the water evaporates, in this case the vapor rises against the gravity to the top, and the condenser is placed on the top, and the condenser is mounted with either fans or fins, so that the vapor condenses on the top, and by gravity the liquid that is condensed comes back to the bottom where the evaporator is. And the section between the condenser and the evaporator is often referred as adiabatic section. The adiabatic section literally is sometimes misleading. There is no, what it means to say is that there is no active process for either dumping heat into the heat pipe or removing heat out of the heat pipe. It is an empty section, but there is no adiabatic condition as such in that region. There could be loss, but it is often referred as adiabatic section. This thermosiphons or Perkins tube are in because they use gravity as a mechanism to recirculate the fluid or the liquid in the system, that they are not quite often used in electronics, because in electronics a user can use a laptop or any device in any direction. So, someone who is using a laptop may put the laptop upside down, sideways, whatever way they like, and so the heat pipe, if used in a laptop, needs to work in any direction one uses, or at least should partially work. If one tilts this Perkins tube, the performance gets affected. So, that is why the shortcoming of Perkins tube is gravity assistance. So, that is replaced if you put a wick on the side or around the wall, that allows the whether it is gravity assisted or not, the wick will be able to deliver the liquid back to the evaporator, provided necessary conditions are satisfied. So, some of the older sections were handled by General Motors, and they were patented back in 1940s, and you can see an image that is shown here on the figure, where there is a wick that is on the bottom, and it is a circular pipe. The wick is annular to the pipe essentially, and the central core of the pipe is the space allowed for the vapor to move from the evaporator end, where the heat is dumped into the heat pipe, and the liquid the vapor is condensed at the condenser, and the liquid that is condensed is brought back to the evaporator by the capillary action here. So, this mechanism, there are two mechanisms that impact heat pipes. One is the vapor flow, that can be depending on the operating temperatures and the fluxes. One can be limiting the operation of the heat pipe because the vapor is moving from evaporator to condenser, that is, it could be vapor transport limited or liquid transport back to the evaporator limiting. So, most of the case, the capillary pressure of the wick or the heat pipe is the most important parameter that often the heat pipe fails, is that if the capillarity is not sufficient, then the liquid never comes back to the evaporator end. So, that makes it challenging, and so a wick, designing a wick is crucial in improving the heat carrying capacity of a heat pipe. So, let us have a look at in some detail about the operation of a heat pipe. So, we will first briefly discuss the heat transfer mechanisms, and then we will look at it from a thermodynamics perspective. From a heat transfer mechanism perspective, what happens is, as we dump heat into the heat pipe evaporator end, there is conduction across that evaporator wall, and then from that the heat is conducted into the wick. So, the effective thermal conductivity of the wick is also important, and then there is latent heat transfer, that is essentially the liquid changes phase from liquid to vapor. Then the vapor condenses at the condenser end. So, there is conduction again across the condenser wall and the wick, and the temperature difference drives a vapor pressure difference in this system. So, if you compare this for the same amount of, if the heat pipe is designed well, for the same temperature difference, for a small temperature difference, heat pipes are able to carry lot more heat than the copper rod, for example. So, that is why the heat pipes are effective. So, temperature differences are small, but they are able to carry more heat. So, the desirable properties of the liquid, because here the charged fluid in the heat pipe is most important, and it should have high latent heat of vaporization, it should have high surface tension. The reason for high surface tension is to improve capillary pumping. Then it should have low viscosity, so that the pressure drop in flowing through the wick for the liquid is reduced, and also it should have high liquid thermal conductivity, so that it reduces the temperature difference in the evaporator or the condenser. So, these are the desirable properties of the working fluid, and in terms of wick characteristics, one desires always, at least at the evaporator end, we need a capillary radius of as small a capillary radius as possible, because the capillary pressure is nothing but the capillary pressure driven is inversely proportional to the capillary radius of the wick. So, 2 sigma by r is roughly as an order of magnitude estimation, 2 sigma by r, sigma being the surface tension of the fluid, divided by r, the capillary radius of the fluid, gives the capillary pressure across the liquid vapor interface. Then the wick should have high permeability, so the liquid flow through the wick, it should have low capillary radius, but high permeability, which is a conflicting requirement in many cases, such that the liquid phase, the high permeability enables liquid phase to flow through the wick with low pressure drop. Since in heat pipe it is a natural circulation driven process, reducing the pressure drop is as critical as anything else. So, it is important to keep the pressure drop at a much lower level, and also the last but not least, the wick should have high effective thermal conductivity to minimize the thermal resistance of the heat pipe. The wick porosity, that is the porosity meaning the volume of the liquid, the void fraction of the medium, wicking medium can also be graded, that is one can have finer mesh, so that it enables lower capillary radius in the evaporator and larger or coarser porosities at the condenser end, where the pressure drop can be kept at minimum. So, if you look at the thermodynamics of this heat pipe, the pressure wise, we will see that at the evaporator end, as shown here in this figure, at the evaporator end, the vapor pressure will be very high, and as it flows down from evaporator to the condenser, the vapor pressure drops, but at the condenser the liquid will be at the highest pressure, and as it flows down from condenser to the evaporator, as the liquid flows down, then it drops to the value of the capillary pressure. The summation of the vapor pressure drop and the liquid pressure drop is equal to the capillary pressure that is enabled in the system or in the heat pipe. So, if you look at it from a temperature entropy diagram, one can look at the evaporator as the line A to B to C, and there is a adiabatic vapor flow that is along this A to, this is from location C to location D, and that is drawn here, that is the adiabatic vapor flow region. From D to E is the condensing region, and the adiabatic liquid flow region is E to A. So, if we closely look at it, one of the important things that we notice is that the temperature difference between the evaporator and condenser is the major driving force. So, the temperature difference, if it is 0, then there is no circulation, because the pumping power that is happening, the natural circulation loop in the system is enabled by this temperature difference. If the temperature difference is large, then there is larger mass flow rate, and that enables more circulation in the system. So, it is important to work with temperature difference between evaporator and condenser that are suitable enough to overcome the pressure drops in the system, and in the process the capillary pressure assists in bringing the fluid back. So, the temperature difference is the main character that one should look at in terms of heat pipe design, even though in many heat pipe textbooks the often quoted design characteristic is to design capillary pressure, that is the 2 sigma by r. So, always people talk from a capillary pressure perspective, but capillary pressure is only one aspect, but the real driving force is the temperature difference between the evaporator and the condenser. So, with that, in a heat pipe, like any other process, the conversion of the thermal energy into fluid flow motion is always going to be less than 100%, and heat pipes cannot operate at uniform temperatures. There is always going to be a temperature difference between inlet and the evaporator and the condenser. So, for achieving higher thermal transport from location A to B, then one has to provide sufficiently large temperature difference. And all these relationships can be established using well known Cauchy-Clapeyron equation and others, but we won't get into the details of those. Instead, what we'll do is that get into some of the characteristics, some of the wicks that are often used, and some details of the heat pipes little bit more because of the shortness of time. So, we look at capillary wicks for heat pipes. The wicks, there are many different types of wicks. The simplest of all is providing a groove. These grooves are like micro channels. These grooves enable the radius of the groove is the capillary radius of the heat pipe. So, you can calculate easily the capillary pressure that can be enabled from this. One can put a mesh, a screen mesh, or one can put sintered particles, sintering copper particles as a wick in heat pipes. These are much more, the sintered meshes or sintered particles wicks are quite common these days in modern day high performance heat pipes, and there are many other varieties that one uses. So, in terms of capillary pressure, as we talked about, the capillary pressure is modulated by the gravity, and the gravity, if the heat pipe is placed horizontally, is equal to 0, but if the gravity can oppose the capillary pressure or assist depending on the orientation of the heat pipe, and it is balanced by the pressure drop in the liquid region and the vapor region. So, in order to achieve maximum capillary pressure, then one has to design in such a way that these liquid pressure drop and vapor pressure drops are reduced, and so we will look into the shapes and the contact angles that enable these better performing heat pipes. Is that one always gets a capillary pressure if written in with respect to the contact angle, then the expression for capillary pressure is nothing but 2 times sigma, sigma being the surface tension, and cos theta E, E is the contact angle made in the evaporator section, and Rp is the capillary radius of the wick, and minus cos theta C, which is the contact angle made in the condensing side. So, in order to achieve the maximum possible capillary head, one would like to have cos theta C being equal to 0 and cos theta E being equal to 1. So, if that is, then one can achieve the highest possible capillary head. So, this is achieved by many ways, or one can try to achieve this by modulating the wick structures. So, in terms of heat pipes, there are many limits that are often quoted in textbooks, and they are called as capillary limit, sonic limit, entrainment, boiling, and viscous flows. These are mechanisms that happen. What we mean by that is that heat pipe ceases to operate when it reaches a capillary limit. That is, if the liquid that is condensed at the condenser is not able to reach the evaporator, then because of either higher level of vapor generation in the evaporator or for some other reason that the capillary wick is not able to pump the liquid back at the rate at which vapor is being generated, then it is to be called as capillary limit. In a sonic limit, the vapor flow is such that it is so high speed that it has choked. Essentially, the Mach number has become 1. So, that is the sonic limit. Because the vapor and liquid in the condenser are going in or traveling in a counterflow direction, the vapor, if it is at very high speed, it can entrain some of the liquid from the condensed liquid that is flowing in the wick. So, that is the entrainment limit, that is carrying back the vapor liquid that is condensed back to the condenser itself and not allowing the liquid to reach the evaporator. And if there is boiling that is happening in the evaporator section, sometimes the bubble that is generated creates lots of dry spots and does not allow liquid to reach those nucleating sites. So, that is the boiling limit. And sometimes viscous forces, if you are operating at very low temperatures, the viscosity of the liquid, for example water, may be very high, close to its 0 degree C freezing point. So, that may be often termed as the viscous limit of the heat pipes. So, all these limits establish what is called the outer periphery operational limit of a heat pipe, as shown here. So, viscous limit happens at a lower temperatures, sonic limit comes at relatively low temperatures, but still higher, then the capillary limit, the entrainment limit, and this is the boiling limit. And if you actually test a heat pipe as a function of operating temperature, and if you plot heat transfer rates, then the curve looks like it. Essentially, you will obtain a linear curve. That means it can be fit with the conduction type expression. The heat transport is nothing but K, which is a function of temperature times delta T, the temperature driving forces, and this CD is the modulator that gives us the effective thermal conductivity of a heat pipe. So, with this way you can think of heat pipe as a better heat conductor from point A to point B, because it has a linear characteristic. And this is an example of how a resistance network will look like for a heat pipe. If you have a heat source, there is a contact resistance of the heat source with the heat pipe. So, there is an external resistance, then there is conduction in the wall of the heat pipe, and this partially there is a parallel conduction through the wall all the way to the condenser. Then there is a resistance in the wick, resistance or axial conduction in the wick as well, and then another resistance from the wick to the vapor, and then from the vapor space there is an additional resistance back to the condenser vapor to condenser liquid, then condensing side wick thermal resistance from the wick to wall, and then to the external part where there is a heat sink. So, that is the entire resistance, and often these are simplified to simple problems, and using the pure conduction resistance one can approximate, at least as a first order approximation, assume that heat pipe have a thermal conductivity of 100 or 1000 watts per meter Kelvin instead of trying to do all these resistances. There are many different types of working fluids for heat pipes depending on their operating temperatures, and they could be helium, hydrogen in terms of cryogenic fluids. It could be ethanol, water for moderate temperature fluids, and even heat pipes use metals at high temperatures like cesium, potassium, sodium, and so on to enable them at very high temperatures. There have been demonstrations using lithium up to 1800 degrees Celsius. So, these are a quick review, and these heat pipes take another form called vapor chambers in electronics, where you are severely limited by the spreading resistance of the structure. That is, if you have a very high heat flux device, but the surface area of the device is very small, then is spread through a vapor chamber. That is, a vapor chamber is very similar to a heat pipe, except that now the evaporator is placed close to the heat source and the condenser is placed on the top side of the heat source, and a wick is enabled to return the liquid back to the heat source. So, this is the vapor chamber that is often called as vapor chambers in heat pipes, and they are used, or so many commercial products of these are coming out in the market for cooling electronics. And we won't get into the details of this, and there are also others where you can modulate the performance of the heat pipe by using what is called gas loaded variable conductance heat pipe, where you provide a heated reservoir of a non-condensable gas. As you heat the gas, the non-condensable gas pushes and moves the liquid. So, this condensation region is modulated by using when you heat it, the non-condensable gas blocks the vapor from penetrating deep into the condenser region, and only part of the condenser region is used. So, in this way you can vary the conductivity of the heat pipe, and if there is no heating, the non-condensable gas stays in this reservoir so that the vapor can penetrate all the way. So, if you want very high, so when you want to use precision temperature control like in optoelectronics, then these gas loaded variable heat conductance heat pipes can be used to so that you can keep the temperature at constant temperature of the device at a given temperature. With that, we conclude a very short description of heat pipes.